Hi everyone, my name is Sam Wish, and today I'll be talking about converting a scattered light microscope into a reflected light microscope for quantum materials outreach. And the first thing I want to do is kind of motivate our study of quantum materials. And really what it boils down to is that quantum information science needs devices that can compute faster with quantum algorithms and qubits, right? So quantum computing. We need to send information securely via quantum communication, whether it be photon or other means of quantum communication. And then we also need to measure things with greater speed and certainty, right, with quantum sensing. So we can have greater precision, we can measure things faster, right? But really what we need, and all of these devices need materials that will exhibit quantum phenomena. And one class of materials that can do this are 2D materials, and there are thousands of them with all kinds of material properties, whether it be they can be semiconductors, semi-metals, metals, ferroelectrics, insulators, right? You name it, they got it. There's a plethora of research out there that's working on stacking them in an endless amount of combinations to create so many devices. And 2D materials could be what we're after for, you know, our quantum materials to answer the problem or to get to the root of the problem for quantum information science and the need of these devices. So, how do we get people interested in quantum materials? Because this, or in 2D materials, because this field really is only 10 to 25 years old. With this primarily with the study of or with the discovery of graphene. Then you had the study of MOS2 and the direct bandgap semiconductors in the early 2010s, right? And so this is a really new field. And how do we attract future researchers? And the answer is we have to show them cool stuff, right? And the way we kind of do that in the lab is with these with our scatter or with our reflected light microscopes. But the issue is that we can't put a reflected light microscope like this Olympus BX53 in every K through 12 classroom or science room in the United States because these things are $20,000 to $40,000, right? They're high-end scientific equipment. They're the cost of a car. Teachers can barely afford markers. So how can we let give teachers an opportunity to teach about 2D materials, quantum materials science, and get people interested really in talking about quantum. And so what I'm proposing is that we take a scattered light microscope and we convert it into a reflected light microscope. And so let's start with this scattered light microscope that we want to adapt, and that's a Carson MM Microbyte Plus. You can get these on Amazon for about $15. That's great, very affordable for our teachers. And it has 60 to 120 times magnification and an adjustable focus, which is a great kind of tunable knob for all of the optics that we plan on mounting on top of this thing to turn it into our reflected light microscope. So just kind of looking at some, I guess, device performances of this thing, kind of out of the box. So here I have a sample that has some pre-patterned gold electrodes on it. And these are separated by about 20 microns. And so we can kind of make that out right now here with our eye. So we can say that, hey, our, so I guess, this thing it'll meet the bill. It'll be able to see, it has the resolution and the capabilities of looking at, 2D crystallites that are on the order of anywhere between 20 to a couple hundred microns in in area. So how do we want to convert this guy? Well, what we want to do is we want to put essentially 3D print some housings and put all our optics on top and couple the light in through this illuminator, right? And that consists of a USB light source, a convex lens, a plate beam splitter, and a 3D printed aperture, which I'll get into why we need this aperture in a moment. Briefly, right, our USB light source could be something as simple as these USB night lights. The convex lens, what we really envision in the future is using like an off-the-shelf classroom-style plastic acrylic lens that anyone can really afford. They can come in packs of 20 for like $16. That's great. And then like a plate beam splitter. I found some examples on eBay that'll go for about $4 for something that's about 30 millimeters and across the diagonal. So pretty good size. And then ideally, what we can do is we can put that in a 3D printed housing and incorporate our 3D printed aperture kind of into the base of that we'll then put on top of our Carson. For our tube lens up at the top, so that we can get the image that's coming out of the microscope, passing through our aperture, going through the beam splitter, and then going through our two convex lenses here to our observer up at the top underneath conversion. What that'll take is our two convex lenses, beam splitter, 3D printed aperture. Hopefully, ideally, we're going to use the same convex lenses to really simplify the cost and the manufacturing of this. The plate beam splitter, same guy, and the aperture does the same thing. So I'll go over briefly our design goals. Requirement 1, all lenses in the system are going to be plastic. They don't have to be the same plastic, but hey, it would be preferred if they were, right? So we can save cost. Requirement 2, lens volume. We should try to minimize that. So we don't want big, thick lenses because we want to minimize cost. And if we're going to pay someone to injection mold all these lenses and we're manufacturing them on the thousands, less plastic, less money. And then finally, the lenses should have some kind of brim on them so that we can put them in like our 3D printed housings more easily. Now, optical performance objectives. I want to keep the illuminator small, so I want to keep it under 15 centimeters in length. I'd like to NA match the Carson's optics, which I measured to be about 15 degrees. So that means that the image that's kind of coming out of the top of our Carson comes out, forms a little triangle with the apex of about 15 degrees, 30 degrees. And then I want to minimize back reflections from the Carson's eyepiece. It's a flat piece of what I'm assuming is acrylic. So in our kind of prototyping that we've been seeing is that, there's a lot of back reflection that just kind of muddles out anything that you can see actually coming from the microscope. And what I want to do to kind of work with this is just use some kind of small stop, since the microscope already is kind of producing an image at an angle. If we can put some kind of stop to minimize back reflections, I think that's going to be the easiest way to solve that problem. And then let's have an eye relief of greater than 2.5 centimeters, so we don't have to strain our eyes or be really close to the system to use it. So let's start about the illuminator. So I'll talk about the object here, which is our USB light source. Because we're stopping everything down to about a 3 millimeter in diameter aperture, which is something that we can 3D print. That's kind of why I picked 3 millimeters. Big enough, should work. We're not going to use the entirety of the USB light source, which is about 1 inch in diameter. We end up only using about 10 millimeters of it, or 20 if you include the full thing. But we don't use the full. We're not using the full, height of our source. We have here our lens, which we can see I've incorporated some little lips on the edge so we can fit it in our housing. This is a 40 millimeter focal length lens. That's what I've kind of specified. And our object is spaced 80 millimeters from our lens. So I've kind of kept our illuminator under that 15 centimeter kind of threshold. Then we have our beam splitter. For the illuminator, I've modeled it as a mirror for simplicity. But in effect, it's going to do the same thing. And then we have our image plane down here and a dummy image surface, which I'm using for the coordinate break, which I'll kind of get to when we get to kind of the lens data at the end of the presentation. Looking at the spot diagrams and some tolerance offenders, we can see that all of our spots are pretty nice. We have some interesting kind of aberrations going on for the higher order fields for this 5 millimeter object field, but overall we're pretty tight and similar in size. But we're not diffraction limited, and I think that's okay because really all we're trying to do is get light from the USB source into the microscope. And with this kind of 60 micron spot size, we can do that, right? We'll get through our aperture, and we'll all of these fields, right? Everything from 0 to 5 millimeters, that'll easily get through our 3 millimeter aperture. Tolerance analysis, biggest offender, right, with one lens is going to be decenters of X and Y of the lens, and so the resulting like 200 micron shift, which is about the resolution that we can 3D print with a nice printer, results in an RMS spot size change of about 680 nanometers, so fairly small. Overall, not a lot of change from the tolerance, or not a lot of issues with, I guess, with tolerancing. I think the illuminator should be very, very straightforward to build. And the Monte Carlo mean spot size was about 54 microns, kind of going through more tolerancing. The eyepiece design, right? We're saving money. We're using the same two lenses, so now we only have two parameters that we can adjust. The distance between the beam splitter, now modeled with BK7 glass, and the spacing between their two lenses. And for my merit function, I'm using the default spot size merit function and only an effective focal length. And I just wanted that so that I can put my object roughly 5 centimeters away, and then I can get an image formed. I know that will be more than 2.5 centimeters from where I want to form. So here, right, and so I flipped it. So now our object is on the right and our image is on the left. But yeah, with only two parameters to adjust, there's not a lot that the optimizer can really do. But it didn't really have to do much, right? So I still think that these are nice spots. While not diffraction limited, I still think it'll work for what we're trying to see coming out of our eye, or going into our eye. So we have a 33 micron spot size for the on-axis field, and then a 63 micron spot size for our 5-degree field coming off. Now, what I want to point out is that the MTF is fairly poor. It is just poor. It's not good. And that could be a problem because the nominal size of our 2D crystallites lies kind of in this range. And I'll show our 20 micron kind of, this is about where our 20 micron spot is, or our 20 micron separation is, which corresponds to a cycles per millimeter of about 50. So not great. So this could be a problem, and it might not allow our students to see smaller crystallites, but I think this is something that I would just like to build and test before I go out and really optimize more, because if this is good enough, that would be great. And I don't really know what I need in terms of this, right? Because this hasn't really been done before. But for tolerance analysis, the biggest culprit was the tilt of the beam splitter. Then following that was the distance from the beam splitter to lens 1, so it's going to be the rightmost lens, and then was the lens separation. And this results, all of these kind of maximum, this resulted in an RMS spot size variation of up to 6.4 microns, fairly large, but I think overall still kind of within our means. And the Monte Carlo mean spot size was about 54 microns, so I think we're still all right there. Going over the lens data, the one thing that I'd like to talk about that I kind of learned about was the use of the pickup solves for the coordinate breaks. One nice source is the flip mirror module that comes from Zemax. And then also using a chief ray solve for the coordinate breaks, right? And so what these decenters are really doing is they're adjusting the position of our beam splitter up and down and Y so that we can kind of get the center of our beam splitter, which is about what we're kind of expecting for our stuff. And with that, I'd like to kind of talk about successes, failures, and conclusions. So we've created this illuminator and tube lens arrangement for this microscope, and that's really nice. The illuminator definitely meets the design criteria, so it's looking great. Everything was made with the same lens too, which is what we wanted. But the tube lens has adequate spot performance, I believe, but the MTF is probably too low to see our smaller crystallites. So we need to improve this, right? And I think the first thing we're going to do is get rid of the same lens everywhere, and then it allows us to change materials and surface curvatures, and we can really get some good lens bending in there. So thank you.